total ballgame.
I'm gonna pray calculus. Good evening, stream. I am very excited today. We are doing math. Like, math. And so for those of you who don't know, Penn Center and I have been working together loosely, at least in terms of like advertising and collaboration and stuff like that, to do a math course. And so I'm going to be, over the next 12 to 13 weeks or so, going through like a series of topics and a series of material that should help kind of give you all sort of like a grasp of calculus. Spooky 13 weeks of math, that's right. And so it's been awesome. A ton of people have joined the server, as of late. Is it funny or depressing that I'm an IT dropout solely because of math? I mean, it is what it is. Hopefully, so the whole kind of idea for this whole course, and with the idea of it being like an exploratory math course, is what I'm like trying to do, what I'm trying to work towards, is to essentially pose a series of questions and give you guys a series of baseline material, so that as we kind of continue to go through the topics and we continue to build things up, you guys will almost be able to stay like a step ahead of me. You'll be like, oh, sneaky Talos, I see where this is going. And then you'll be able to use what we've talked about to essentially, hopefully like predict what we're gonna do next. And so today we're just doing pre-calc and trig review. I've got some notes here. I've got a series of things that I want to go through. And the first thing that I kind of want to just hit is essentially, we'll go right back to the beginning of algebra. Kind of where I want to start is like, what was the takeaway from algebra? What were we doing? And like, what's the point? And so I hope everything looks all right for stream. Here, let me turn these grid lines off here. My thermal systems professor taught in a similar way, and that was one of the easiest classes to ever understand. Hell yeah. I'm studying IT, the math is pretty fun. I think this is going to be awesome. I think this is going to be great. And so, the first thing that I kind of want to get at here, let me get ready with some music. I need to make sure that it's nothing that's going to get like this VOD muted. That would be so annoying. Alright, let's bring this music down. And we'll get some of this stuff going. Stardew Valley, anyone? I enjoy math, but in very particular cases. We'll just, sit back, relax, and we'll lead the way. And so, naturally, so kind of like one of the first things that you kind of learn in math is all just like about, or in algebra specifically, it's just about like graphing. And so when it comes to like plotting a point, we know we have like the coordinate plane, where usually we're graphing x versus y. And so one thing that I immediately want to challenge, just kind of like with baseline level of like algebra knowledge, is that it's not necessary at all to graph x versus y. X versus y is just kind of like the very generic, it's like what you see most often. But, we can talk about some function of time, where, something changes with respect to time, and, we'll get to that, where it's like, distance over time and velocity and stuff like that. Yeah, you could even graph y versus x, where y is horizontal and x is vertical. Or, you know, it's instead of describing x as just like some abstract variable, we can describe this axis as time. And maybe this axis could be like our distance. And so our distance with respect to time and stuff like that. And so the x versus y is just kind of like an arbitrary choice, a matter of convenience, just so that we all have kind of like a baseline level of something to talk about. But it doesn't have to be like that. And so that's just one thing that I kind of want to challenge straight away. It's not always just about x versus y or an input. Well, it's more than like x versus y. It's more kind of about like an input versus an output. We have some input value, x, that usually graph the independent variable along the horizontal axis. And for plugging in x, we get some output value of y. And so like if we had something, you know, a very simple function, like we said y is equal to x, then basically what we're saying when x is equal to 0, here if I make a table here, then if x is equal to 0, then y is equal to 0 too. Or if x is equal to 1, then y is equal to 1. And when x is equal to 2, then y is equal to 2. And then we can go along and we can graph these points. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. And so on. This is very familiar to me. Don't worry, we're going somewhere with this. And then we can have more complicated functions too. Like, you know, say for instance, if we have something like y equals x squared, or even, you know, steadily more and more complicated. Are you currently recording this for the math course? Yes, this is also being streamed on YouTube right now, and all of these streams will be put into a playlist that I will share in various servers. Are you currently recording this for the math course or just developing it? We're live, baby. This is it. This is it. But yeah, if we have something instead, like y equals x squared, well then we can imagine kind of what happens with those points too. If we have 0 squared, it'll be 0. If we have 1 squared, that's 1 times 1 is 1. 2 squared is 2 times 2 is 4. And so on. And so if we imagine graphing those points, we start to get kind of like a different shape. And so what I've built here is a Desmos graph that kind of allows us to see the effects of, you know, plotting more points in a region and what that kind of does to like the shape of things. And so we can see that if I have a function that's x squared up here, then with only 5 points, then we can start to see kind of maybe the vague shape of the graph as it goes up like this. But if I increase the density of the points... Chat is not on YouTube? You can't chat? You should be able to. Or did I break it? I don't know. Enzo's Creations, welcome in. You should explain why a and b are used when the function is x and f of x or y. Yeah, so in this case, a and b are just supplemental variables. And for Desmos, it does kind of follow the convention that we're graphing x is on the x-axis and y is on the vertical axis. Or rather, x is on the horizontal axis. And so here, I should explain, when we have f of x like this is function notation. And so function notation is something that we basically use to talk about various different equations. And so if I have something like up here where I wrote y is equal to x squared, another way that I can describe this is f of x is equal to x squared. And those of you kind of relatively familiar with algebra, but not too familiar, might get confused by this sometimes, where this right here looks like juxtaposition, where you might have a variable f times the variable x. but it's different. And sometimes you do just kind of have to pay attention to the context, where usually functions are kind of described explicitly as an equation. And so what I mean by explicitly is you have f of x on one side equals something else on the other side, and that something else is the function. And so the way that we describe this is that f is the name of the function. And so we would say we have a function f, and then this function has an input, x. And so x in this case is our input variable. And so if I wanted to use this function for something, then I could say, okay, well, what's f of 3? And so now basically what I've said is, okay, what do we get if we replace our input everywhere it shows up in the function with 3? And so that would be like saying we're going to take x squared, but we're going to replace every instance of x with 3. And so that would just make this 3 squared. And 3 squared means 3 times 3. Wow! Who did that? Which means 9. And so f of 3 is 9. And so you gotta find for x, and then you would do the same for y, I believe so. Yeah, so well, in this case, and so this is kind of, you know, what I was talking about earlier, where it's like challenge your notion of graphing x versus y. Really, it's kind of like you have an input variable versus an output variable.
Shit, you didn't turn off the funny noise machines. Get talked over, dummy.
That's right. We still get to have fun around here. And so in this case, what we're really talking about, if I change this from y to f of x, and I say, okay, let's instead of graphing x versus y, let's graph x versus f of x. And so now this isn't our y-axis anymore. This is our f of x axis. And so now instead of thinking about this in terms of input like x versus y, it's still, again, you know, the best way to think about it is like inputs versus outputs. If we have x equal, if 0 comes in as an input, then we get 0 out as an output. If we put 1 in as an input, we get 1 out as an output. We put 2 in as an input, we get 4 out as an output. And so that's kind of what I'm demonstrating here, where there's kind of this idea, though, where it's like you kind of start by plotting points to figure out what functions are. But, you know, unless you can somehow plot infinitely many points, how are you exactly sure about the function? And so, but kind of beyond that, injectivity, surjectivity, bijectivity, it's just kind of this idea where as you kind of plot more points for something, especially once the functions become non-linear, you can get a better idea of what the functions look like. So for something like x squared, I've made this graph so that I could plot a whole lot more points. And so we can see if I crank this up to like 300 points, it looks like a solid line. Are you? And you can see that if I widen the bounds on this, so if I make a lower, then we can see more points on this side. And so this is an iconic shape in algebra, typically. This is a parabola. In algebra still? Well, cool. Hopefully you'll be able to follow along. Hopefully this doesn't, you know, we don't outrun you too much here. And so you can see here, as we have more points, we can see the shape of a graph. And, you know, it's the same sort of thing where if we just have x, with very few points, we can still see that kind of like, okay, this looks like a straight line. But as we increase the number of points and make it more dense, then okay, we can kind of confirm it looks like a line. Or if we have something like the absolute value of x, then you can see, okay, well, if I only look at the positive side, then it looks like a straight line, but the absolute value of x does this thing where as it becomes negative, it kind of flips and continues, and has this sort of V shape. And so on my Discord, in the mathematics, or the math zone, I made a post that should have the link to all of these Desmos graphs if any of you want to play with them yourselves, including some of the ones that we're going to be using later on in the course.
What are your thoughts on algebra?
I bet Evil Talos loves algebra. And so, where we're kind of going with this...
Oh,
I'll let him talk.
algebra. You mean the delightful torture device every math teacher uses to unravel the minds of students? It's absolutely essential for life. Much like a quest for world domination plus...
He used
you can use it to
emojis.
calculate the trajectory of flying gnome projectiles. And remember, chat, you're all terribly cute. Now, if only I could get 7 or a secret hand-holding buddy to reach that evil plan on top of the fridge. Curse you tall fridges and your smug shelves.
Your smug shelves. And so, one of the important takeaways from this is to kind of develop an intuition for what different functions look like. And so, if I have, x looks like a straight line. If I make it x squared, it's this parabola shape. If I make it x cubed, it's this almost kind of like S-curve shape. If we keep going and I do x to the 4th, oh, it's kind of like a parabola again, but now it's kind of like flatter at the bottom and steeper on the sides. If we do x to the 5th, then it's kind of that S-curve again. And it just kind of keeps going like this. But there are other types of functions that are important to know too. Like if we have like the square root of x, then you can see that this function kind of does its thing over on the right, but there's nothing over here on the left. That's interesting. Or we also even have logarithms. And so logarithms are like the inverse of exponential functions. And we'll talk briefly in a little bit about what it means to be an inverse. Or there's also exponential functions. Like if we have e to the power of x. These are because the degree of the function is directly related to the number of curves, right? I guess it depends by what you mean by number of curves. And so, if we're talking about like polynomials, if I plug in something like x plus 1 times x minus 1 times x plus 2, then if we were to multiply this all out, the degree of this function, that is to say the highest exponent of this function, would be x to the power of 3. And the fact that it has x to the power of 3 means that it can have 3 solutions, so 3 values that would make the function equal to 0. And so you can see it crosses the x-axis 3 times, here, here, and here. And the number of solutions that are possible is related to the degree of the function. And so, at least it is to say that it can't have more than 3 solutions. Now, it could have less than 3 solutions. Like if I get rid of this x plus 2, but I make this x minus 1 squared, then this is still a third order polynomial. It's still a polynomial whose highest degree is to the power of 3. I lost now? Okay. Well, I guess let me continue. But you can see that this still only intersects the x-axis twice instead of 3 times. The number of solutions includes multiplicities and imaginary solutions. Correct. Yeah. And so this is just kind of like, like just talking about like different functions and understanding like what functions look like and how to kind of work with them is really sort of important. There are technically 3, that's correct, because since the x minus 1 root here occurs twice, then it's like you could say there's 3 solutions, but it's just like 2 of them are where it intersects the x-axis at 1. But, ostensibly that's really only 1 solution. And so you could say that the number of real solutions a polynomial has are less than or equal to its highest degree. But yeah. And so, kind of where, like the important thing to know kind of about this is like how all the different functions look. You don't necessarily have to memorize it, but you can kind of build up an intuition for it. Like if we go back to our humble parabola, then we can kind of ask ourselves, okay, well, like, why does it seem to have this shape? Like, what if we ask ourselves, it's like, why does it look like this? And so we can think about, okay, well, what happens when the values are small? Like if they're between like 0 and 1. And so if you have something like 0.5 squared, then if we say like x is equal to 0.5, and so f of x, or rather, I guess I should say, f of 0.5 would be like we have 0.5 squared. And kind of the takeaway is that if you have something between 0 and 1 and you square it, it gets smaller. And so like 0.5 is like a half. And so if you have a half squared, that's a half times a half, which is a fourth, which we could also describe as being 0.25. And so that's another kind of important intuition to kind of build up over time. Like, when is it basically that you're going to see that numbers continue to get smaller versus like when do numbers continue to get bigger? And so if we reach the point where like x goes beyond 1, and so once x is larger than 1, here, let me turn on this, just the line here. And so when x gets larger than 1, we can see that the values start to get bigger. But between 0 and 1, it's kind of like they grow slowly. And then as we go further beyond, they grow faster and faster because those values are getting squared. Similarly, if we look at something like x cubed, then, you know, if like 0.5 squared is small, then if you have 0.5 cubed, then that's even smaller. Because then you have like 0.5 times 0.5 times 0.5, which will be like an eighth, and that's 0.125. Hi, Dawn. Welcome in. And so kind of the idea here is, you know, you want to memorize the parent functions, and you want to be able to know, it's like, okay, whenever they say that you're working with this function, it's really good to have kind of an idea mentally in your mind of what that function looks like. But if you cannot like immediately remember it, well, then you can kind of fall back on this intuition of like, okay, well, for this function, between this, pardon me, between this value and this value, it's going to grow slowly, or the values are going to be smaller than the input. Whereas beyond some value, they might grow faster than the input. And so like if we go out to 2, you know, on this function, well, 2 cubed is 8. And so it shoots up all the way to here. Whereas 1 cubed is just 1. And so if we go down to where x is 1, and we look at the graph, well then we get 1, 1. But then like I said, between 0 and 1, then the outputs are actually smaller than the inputs. And then there are functions where it's kind of like the opposite, where if we go back to like the square root of x, here the inputs are often larger than the outputs if we're greater than 1, because usually the square root of a number is less than itself. Whereas between 0 and 1, the inputs are actually larger than, or smaller than the outputs. And so it's just kind of, it's good to have like this intuition for functions. And so kind of going beyond that, something else that I want to take a look at too. Here, let me just open another Desmos. Bork. And so something else that I want to talk about is kind of like transformations of functions. And so those of you who you might remember from algebra, when talking about graphing parabolas and things like that, there was a form of the function where if you have like f of x is equal to a times x minus h squared plus k, this is called the vertex form of a parabola. And so this would be like vertex form. And here, oops, I wrote h twice. A, h, and k all kind of have specific meanings or specific functions. Where usually like a makes the function taller, it stretches vertically. Whereas h and k together kind of make up the left / right and up / down transformations. Down.
Bro, imagine being vertically stretched. Wish that were me, so I can get my fucking plans off the fridge.
And so where it ends up transforming, like shifting it to left and right, is it basically like you can imagine it moves the origin from 0, 0 to the point h comma k. And so like if h is 2, then it moves it to the right 2. If k is 3, it moves it to the right 3. But this is actually something... Oh my god! This is actually something that works more in general, beyond just like the vertex form of a function. And so we can actually take any function, and so if we say like f of x, you know, let's say we have some function f, then we can say g of x is a transformation of the function if we can describe it as, or I should say a linear transformation of the function, if we can describe it as a times f of b times x minus h plus k. And so in the instance where f of x is x squared, so if f of x is x squared, then we would take that and we would pretty much plug that in here, and then we would take the b times x minus h, and that would go in here as our input. And so then what we would end up getting from that is that g of x is equal to a times, and then it's all of this stuff squared. And so b times x minus h, all squared, plus k. And so this works for any function, and we're going to talk about kind of what a, b, h, and k all really do, and that's what I've got this for. And so I made another Desmos graph all about linear transformations, and so you can see here, f of x is our parent function. We can describe g of x as a linear transformation of f of x. And so, finally something simple and useful I can watch in very chill mode. Yeah! I hope you can just sit back, relax, grab a drink, grab a snack, and prepare to have your mind expanded. And so, I wrote here, kind of like I said here, h and k together represent the left and right, as well as the up and down transformation, from the origin to h comma k. And so, you can see here, we started with x squared, and so we've got our humble parabola. If I increase or decrease h, then we can see as it increases, it goes to the left, I'm sorry, to the right, and as I decrease it, we go to the left. And same thing, if I increase it, or if I increase k, it goes up, and if I decrease k, it goes down. And so we can take our function, and we can pretty much just move it to wherever we want. And so, what, you want it to be over here? It can be over there. You want it to be over here, it can be over there. You just gotta basically change it. You know, where you're going to have these values of h and k in the function. Here, give me 1 second. I gotta let Ate in. She's meowing at the window.
How does it feel to be so short?
Ate here to save me. Katie's being crazy.
How does it feel to be so short?
Hi, Wesley. Okay.
The height complex question asked by none other than Intelligent Fool. Our original being 2 feet tall is absolutely fantastic when you're plotting world domination, especially when things like evil plans end up just out of reach on the fridge. Luckily, Seven's tall enough for the job, if only the universe wasn't conspiring with Sev to make things adorably difficult. And speaking of, where's my banana milk? Yep.
He's coping. He just wants to believe it's great being short. And so let's think about this for a second and think about why h and k actually end up giving these transformations. And so if we just have something really simple, and so if we have f of x, if we say like y is equal to x, or no, I'll write it like this: f of x is equal to x. Then we know that this will just be like a linear function. It's a straight line. However, if we say g of x is a transformation of this, where we say g of x is equal to f of x, but then we just say, I don't know, plus 2. Oh my gosh, there's a battle happening in chat. And so if we have, say, like f of x plus 2, then what do we get here? And so f of x is our output of our original function. And so it's the output. And we take that output and we just add 2 to it. And so that's going to take any value on the line. And so if I just have this be f of x equals x, and I set h equal to 0, and I set k equal to 2, then orange is our original line. And so if we look, say, for instance, at when x is 5, y is 5, and so we take that point at 5, and when we transform it, we add 2 to it. We take that output and we add 2. And so that's going to shift it up 2. This is math. The redeem follows linear growth. That's right. You can calculate the entire amount spent as a triangular number times 5. This is representation at its finest. Dude, this is crazy. How high are we gonna push it? How many points do you guys have? And so there is something kind of to think of, and that's kind of like a little bit different whenever you talk about changing h. And so I think here, it's relatively clear to see that if g of x is basically just f of x but plus 2, then f of x is like you take our output of the function f, and then you're going to add 2 to it. And so however high it would go, it goes that high but 2 more. And so if I change it from, you know, k is up to 3, then it would take whatever the function would normally output, but instead it will go up 3, like 3 higher. I only have 117,000? I mean, that's still a lot of points. How many points do you guys have? Loot was actually one of my, like, top viewers in the Twitch whatever it is, the Twitch replay. Man's afraid to join in with 117,000 points. We just hit 1K on Captain of the Argo yesterday, and now it's 1,200? Was I not one? I don't remember, but you might be. I think you very well could be. More than 150,000. You guys are pulling out all of your money at once. The banks don't actually have the money. You guys are gonna crash the economy. You're gonna go bankrupt. Okay. And so, where it gets a little bit more complicated is when thinking about what does like h really do to the function? Like what does h as a transformation kind of accomplish? Hi Ate, you can't sit here. I need this space. You wanna go on your spot? She's gonna go on her spot, chat. Maybe for a little bit. I get the feeling she won't stay. And so we can see that h kind of makes the graph shift left and to the right. And we can see it here if I turn these points on, because it might look like, especially with a linear function like this, if you increase or decrease k, here, if I turn these actually off for a moment, if you increase or decrease k versus increasing or decreasing h, sometimes it looks like the function's doing the same thing. Like it could be moving up, it could be moving down. It's hard to see, for sure. But if I turn these points on, so we have like the positive points and the negative points relative to where it is at the origin, you can see if I change h, it does actually move to the left and to the right. And if I change k, they do actually move up and down. And so one way that you can kind of think about h, kind of one of the best ways that I've thought to conceptualize it, is imagine that this is like a function with respect to time. And so if h is like 2, then that's like saying we take our function and it's like, to be able, like we're going to subtract 2 from the input. That means to get back up to where we had originally started, when h was 0, we have to get x up to 2 before we get back to normal. And you can maybe see this kind of well whenever we do something like, say, the square root of x. And so k is 0, so we're not shifting it up or down at all. But if h is 2, it's shifted to the right 2, and then you can see there's nothing to the left. This stream has convinced me that we're living in a simulation. How? And so if h is, it's basically like saying we have the square root of x minus 2. And so before x can get back to 0, or before the inside of the function can get back to 0, where the function really starts, then we need to basically take, like we need x to go up, like forward 2 first. And so you can think of like values of h kind of like delaying the outputs of the function. And so it's like you have to go forward further in time before the function would give you the output it would normally give you if h is, you know, if you're subtracting some value from the input of x. Whereas instead, if we're just adding that to the output, well then that makes it go up and down instead. And so we have total control over kind of where to place the function. Now a and b are kind of like a different situation. And so, but we can kind of think about it similarly. And so if I move this off to the side, if we look at this here, or rather here, I'll take this and then copy and paste this down here. Then what we have here is that this is like our output of our function. So this would be our output to some extent, kind of transformed left or right, or kind of moved further or like into the future or back into the past. And then, you know, we can either shift it up and so like add on to the output. Or we can take this output and we can scale it. We can multiply it by some value. And so scale the output up. And so once again, you can think about it. If like our output would normally output like a 4, can I pay anyone here to do my math assignments? We won't do it for you, but you can absolutely post questions and we can always take a look at them. Or squeeze if a is less than 1? Precisely. And so, and more specifically, it's squeezed if a is between 0 and 1, or rather between -1 and 1. And so you can imagine, like, if we take something like x squared, and so I make h0 and k0, then if I want to mess with a, then if I make a2, then what we can see here is that when the function would normally give us an output of 1, well, instead, we take that output and we multiply it by 2, and now we get an output of 2. Or if it would normally give us an output of 4, then we would take that output and multiply it by 2, and so now instead it gives us an output of 8. It's like we've taken all of the points and we've pulled upwards on them so that they're twice as tall. Since when have nerds been so violent? We've always been violent. Just humbly violent. And so if I make a3, then they're all like stretched and pulled upwards by a factor of 3. And so, like Ultimate Doom was kind of getting at, if I decrease a, and so that a is between 0 and 1, then multiplying something by like a decimal makes the value smaller. And so now as a gets between 0 and 1, you can see our transformed function, the blue function, actually gets smaller. It goes down. And so it gets like flattened out. The points get like pulled down on it towards the x-axis. And so I can even do a nice thing here and like animate this. And this is really good because it kind of lets us see the process as the function goes from being positive to negative, which I think is really cool, where you can kind of see it flatten out and flip across the x-axis. And so this is where we kind of start talking about transforms of functions where, you know, it's shifted up and down, left and right, but also like stretched vertically, or like compressed vertically, or flipped across the x-axis. What we haven't gotten to yet is flipping across the y-axis, and that's where B comes in. And so kind of to review here, I do have some notes here on this Desmos graph.
The title of captain keeps flip-flopping. Who's ordering my minions for me?
And so, as I wrote here, A is our factor of vertical stretch, and you can see increasing A above 1 stretches the graph out vertically, and then between 0 and 1 it gets squashed shorter. Conversely, B is our factor, or I guess rather inversely, perhaps. B is our factor of horizontal compression. Increasing B above 1 will squash the graph inward horizontally. And so you can see as I increase B, then rather than the points getting pulled upwards, they get pulled in towards the y-axis. And that's why I have these like points added on here, because it's really interesting. For several functions, it's hard to immediately tell whether something is a vertical stretch or a horizontal compression. And so without these points on here, a equals 4 looks the same as when b equals 2. And you can spend some time and kind of think about why that is, for the fact of like if you have f of x is equal to x squared. Hey Phobos, welcome in. But with these points on here, where I actually kind of set it up so that you can really see that increasing or decreasing b, like pulls the points in towards the y-axis, whereas increasing or decreasing a pulls them in or away from the x-axis. And so now we have basically a framework to take your parent functions, to take the functions that we were talking about earlier, the absolute value of x, the x cubed, the square root of x, all of that stuff. And you can basically describe any variation of this function that you want. You can shift it to the right by 3, and then you can shift it up by 4. And then you can flip it vertically across the y or the x-axis and stretch it by a factor of 2. Or you can compress it horizontally and do all of that stuff. And so you can take any function and kind of manipulate it and move it in a way, kind of like as a framework like this. And so these are linear transformations. There are other types of transformations. But this is what we've got. Are we gonna have to like calculate how many points you guys have actually spent whenever this dust settles here? And so yeah, transformations of functions. And so one thing that I kind of wanted to talk about next, one thing that I kind of wanted to, you know, have you guys sort of think about, or kind of maybe think, like build your intuition for, is what does it like mean, like, I guess, you know, where I should start with this statement is like, math is always about like having, I would say often sometimes like starting with like an intuitive definition for something, kind of like thinking about something in the way that kind of makes the clearest sense to you, and then kind of establishing more rigorous terms around it. And so if I were to like look at, you know, this graph here, like if I was just to look at, you know, our good old friend x squared, then one question that I might ask is like, okay, well, is this graph continuous? And so does it like ever, you know, have like a hole in it or like gaps or anything like that? And moreover, like, is it smooth? And so like an example of a function that, you know, maybe doesn't look smooth would be like the absolute value of x that we were just looking at, where it's kind of got this like sharp point at the bottom here. But it is continuous. Like there's not any holes in it. Okay, Ate, what's going on with you? You got food. You got food. What are you looking for? And so perhaps one thing to think about is what sets these sorts of functions apart. Like what makes a function continuous? What makes a function smooth? And you know, how do you actually like define that mathematically? Like if I have a function that's, you know, like 1 over x that looks like this, is this function continuous? And well, as we go from left to right and sweep through the x values, well, it kind of looks like there's this gap here right in the middle where we jump from all the way down here to all the way up here, and then it keeps going. And so maybe the definition of continuity has something to do with gaps in functions. But then there's the other question of like, well, is it smooth? Well, it looks pretty smooth to me, where if we look at any section of this graph and we were to like zoom in on it, we don't find any like sharp corners or anything. And so intuitively, perhaps it makes sense to like look at this function and say, okay, this function is smooth, but not continuous. Whereas if we look at, again, the absolute value of x, we can kind of think intuitively, oh, okay, well, if we zoom in and look here, well, there's this like sharp corner at the bottom here where it goes from one way to the other way. And so maybe this one is continuous, but not smooth. And so you can have different combinations of that criteria. And as math kind of gets more and more complicated, it's really kind of useful to have these different sorts of criterias to be able to say, okay, well, this function is not smooth, but it is continuous, or it's continuous, but it's not smooth, or maybe it's smooth and continuous. If f prime is not continuous, does it necessarily mean that f is not continuous? I think maybe not necessarily. Hey Talos, I'm helping David order some sushi and then I'll join you in voice chat. Okay, awesome. If we restrict the domain from -infinity to 0, does f of x, does the absolute value of x become continuous? Something I learned the hard way is sometimes continuity is defined as continuous on its domain. And so in some contexts, 1 over x is considered continuous because it's not defined at 0. Right. And so it's kind of more of like, building up that intuition. Again, though, like, to some extent you can look at something and be like, yeah, that looks continuous, or it looks smooth. But yeah, once again, Ultimate Doom's question, if we restrict it from -infinity to 0, does it become continuous? I think you mean smooth. And so the absolute value of x is already continuous. But if we were to restrict it from -infinity, and so if we do infinity, comma, 0, does this work? Okay, I'll just say x is less than 0. Why you no do? Oh, it's because I put it in parentheses like that. There we go. And so here you can see, if we just look at it on this domain, or on this interval, then it is smooth. And so it is smooth on this interval, where, it's just a straight line. And so it's only when we extend it beyond 0, does it become not smooth. But when you kind of take the function as a whole, right, we're not even getting to like derivatives and stuff today, but it's good to think about. Here, let me jump into here. We might be getting Pen in here in just a minute to kind of help us talk about some things. It's 6 a.m. I'm so sorry, the turtle. It's 7 a.m. or it's 7 p.m. here for me. And so we must be on like, almost like antipodes, opposite side of the world from each other. So yeah, so these are all kind of like leading questions, where, we're not necessarily going to get deep into it today, just because, this is like the, pre-calc review section. But these are things to think about. What does it mean to, like, for something to be continuous, or for something to be smooth, or to kind of like look close to a point? Yeah, what's your longitude and latitude? Latitude is flatitude or whatever. I can never remember which is which. Latitudes are the Z levels or equators, and longitude is the great circles. Yeah, just make it like really cryptic. Like the antipode of my location is somewhere in the Indian Ocean or something. I don't know. Probably. Okay, where are we going next in my notes? Oh yeah, rational functions. So yeah, rational functions. So we've talked about, various different parent functions like polynomials. TOS won't allow me the basic right of doxing myself. It's literally in the rules. Do I have an exclamation point rules command? I don't. Well, it's one of the rules for this channel to not dox yourself. I technically can't stop you from doing it, but I can just ban you forever. And I don't want to do that. So rational functions. A rational function is basically just a function where we can describe it as like a function divided by another function. And so like f of x over g of x. Or I guess I should be more specific. A rational function is a polynomial divided by another polynomial. I don't know if the definition for rational functions extends beyond polynomials. It might. But so something like just 1 over x is a rational function. Or something like x squared over x minus 1 is a rational function. And so rational functions have kind of like various different sorts of things that are different about them. And they maybe break kind of the initial intuition that you might have for polynomials. Where rational functions and things like that start to introduce kind of what we call like asymptotes. And so an asymptote is basically, you can imagine like an imaginary line. And so if I get 1 over x on the screen here, it's like you can think as we get closer, or we go farther and farther out on the x-axis, it's like we get closer and closer to the x-axis, but we never really touch it. And once again, this is kind of like another important thing to kind of keep in the back of your mind, where here we're talking about getting closer and closer to something, but how do you mathematically define getting closer and closer to something? Does that have like a rigorous mathematical definition? Just kind of keep that in the back of your head as we kind of go through things here. Similarly, if we get closer and closer to 0, then you can see the function gets higher and higher, and so it blows up towards infinity. But we never actually get to, we never actually touch the y-axis. Are we getting to limits or convergence in that stuff? That's the idea. We probably won't get there tonight. We are converging upon convergence. That's correct. And similarly, we can talk about, if we look at it from this side, if we just look about this section of the function, then as we kind of follow it in on the x-axis, then it goes higher and higher. But something different happens if we look at it from this other side. And so on this side, as we follow it along and we get closer and closer to the y-axis, then it's approaching negative infinity. But it never actually crosses the y-axis, and it never actually gets to negative infinity, unless you imagine like us getting almost like infinitely close, to the y-axis. But it's kind of like, well, once again, it's kind of like, what the heck does that all mean? That's the question we're getting at here. And so rational functions have these things called asymptotes. We can talk about the same thing, like transformations of rational functions. Like if I make h1, oh here, I need to toggle this back on. If I make h1, then we can shift it to the right. And so that would be the same thing as if I had 1 over x minus 1 here. And now you can see, instead of the asymptote being on the y-axis, the asymptote is here at x equals 1. Or if I make it minus 2, then now we have the asymptote here at x equals 2. Or we can even have functions with multiple asymptotes, where if I make this x times x minus 2, well, that means, okay, well, we had the asymptote at 0 when it was x, and the asymptote at 2 when it was x minus 2, and so now we have both of them. We have 2 asymptotes. And so we have this asymptote here at 0 still, and we have this asymptote at 1, or I'm sorry, at 2. And so here we can kind of start to do the same sort of thing that we talked about earlier with like, okay, if with a function like x squared, you know, you can kind of build up an intuition for like, why does x squared look like this? And it's because like, okay, well, 0 squared is 0, and as you go from 0 up to 1, then you'll have the input squared, but because it's between 0 and 1, that makes it smaller. And so here, to get it on screen. So like between 0 and 1, the outputs are less than the input because a number between 0 and 1 squared is smaller than the input. And then beyond 1, they get larger than the input because a number larger than 1 squared will be a larger and larger number. If we kind of put a similar kind of thought process into a function like 1 over x, well then let's start right here when x is equal to 1. And so when x is equal to 1, well, we would have 1 divided by 1. That makes sense. And so as we increase x from here, then that value that we're dividing by gets larger. And as you divide by a larger and larger number, then our output gets smaller and smaller. And so that's why it kind of ends up having this behavior where it's approaching the x-axis. It's getting closer and closer to 0. Whereas if we look at the other end here, once again starting at 1, 1, and so if we have 1 divided by 1, that's 1, that makes sense. But if we go kind of between 0 and 1, well then if you divide by a fraction, if you divide by a value between 0 and 1, that's going to make the value of the function larger. Current total amount of points spent on Captain of the Argo, 271,425. I believe it. Who ended up with it? Did Mish end up with it? Did Mish win? At least momentarily. Won the battle, but not the war. It's an investment. There you go. And so, you know, we can see here that if we go to where like x is 0.5, and so that would be 1 divided by 0.5. And so that would be like 1 divided by a half, which would be the same thing as multiplying by 2. And so then we get 0.5 comma 2. And so as you divide by values between 0 and 1, the output of the function gets larger. And so that's why we can see this behavior that between 0 and 1, the function gets larger and larger. And so as we divide 1 by a value closer and closer to 0, then the value increases. It blows up insanely fast. I'm new to Twitch. How do you get points? You just get points by watching. Sometimes, occasionally, under the chat, there's like a little treasure chest that pops up. And if you click that treasure chest, then you get like 50 points, kind of just like an engagement thing. If you follow, you get 300 points. If you join on a raid, you get 250 points. And so there's a few different ways to get points. How the fuck does someone have 200,000 points watching for a long time? Subbing gives a point multiplier, right, as well. Yeah, if you're subscribed, you get a multiplier on how many points you get. You could describe the amount of points you get as a linear function with respect to time, whose a value is increased if you're subscribed. Its output is stretched vertically by some scaled factor. Twitch is an idle game for streaming, basically. Yeah, I mean, you can think about it that way. Talos putting it all together. That's right. But yeah, basically just, you know, watching for a long time. Like, if you just got here, you can't expect to have too many channel points. But if, you know, we could do like a channel, we could do like what's it called? A bet. Where like there is like channel point betting where, oh my god. Which VC did you want me in? You can just join hanging out, Pen, and I'll drag you up. Yay! Pen's here. I'm good. Yeah, I was just thinking like we could do 1 second, Pen, but to finish my thought, we could do like a channel point gamba. Oh, Pen is quiet. It's because you heard him through my open back headphones because I have Discord muted. Now Pen should be good.
Hi, chat. You all look beautiful today.
It's true. We could do a gamba where it's just like, you know, vote on, like, bet a very small amount of points on this side if you want the rich to donate to the poor. And then if you're rich and want to give people points to the poor people, then bet a whole lot of points on this side. And then we can just, you know, automatically let the poor side win. Have a have and have-nots gamba. Donate to the people with no channel points. That would be funny. Okay, Pen, how are you?
I'm doing good. I have had a fantastic day. I was doing a bingo, hosting bingo at the brewery, and it's always a really fun time.
Hell yeah. And so we have been making our way through some
Making your way
pre-calc.
downtown?
Yeah, exactly. And so what I've covered up to this point is we kind of briefly talked about plotting points and functions and different parent functions and kind of talking about, you know, the intuition that you might use to kind of think about like what do different functions like look like and why. And kind of building up from there, and now we're kind of working on rational functions, and we've talked about transformations and all that sort of stuff. We haven't gotten to any trigonometry or anything yet. And we've kind of touched briefly on just like intuitively, if you look at a function, you know, does a function look smooth? Does it look continuous? What does that mean? And kind of keep in the back of your mind, like, how would we work towards defining something like that mathematically?
Very cool, very cool. I love it.
And so do you have anything that you want to throw in there?
I was gonna ask, like, how has chat been? Have they asked some like really hard questions to you?
Not yet. Do you want to ask? So one question that did come up when I was originally talking about that stuff was kind of the idea as well that sometimes continuity is defined as something being continuous on its domain. And so something like 1 over x is sometimes considered continuous just because it's not defined at 0. Whereas
okay, yeah.
But that would mean things are only that would for the most part only mean that things are like discontinuous whenever there's like a sudden jump in the value, but it's defined at every point.
Right, like a step function in electronics or something like that.
Exactly. But I don't know. I would say intuitively, something like 1 over x feels not continuous. But I guess I maybe don't 100%. I mean, I guess it would be a good chance to kind of take a look at the book and see what kind of definition the book uses for continuity.
Yeah, I guess I would ask what. So what about it makes it feel like it's not continuous?
Well, it's the fact that, it goes from one value kind of shooting off towards negative infinity to jumping over to being like almost at infinity and then coming back down. And so it's like you go from one value suddenly to another radically different value.
Yeah, okay, yeah, I understand what you're saying. So there's something about at a particular x value, almost like two outputs or something like that.
Right.
I'm being
Right.
super non-mathematical in how I'm talking about this.
Right, and that's kind of where we're sort of beginning with this anyways. We're not trying to necessarily get too deep into like math jargon, but we're just kind of trying to like rationalize feelings about functions in a way.
Yeah, and I think what I'm hearing from you is there's something about a break in the function that feels concerning.
Right, the asymptote. We have talked about asymptotes. So yeah, what did I have planned next? And so I guess from here, and so I don't know that there's too much. So we kind of like talked about functions, transformations, all of that stuff, polynomials, that sort of thing. Is there anything that's kind of in maybe like the non-trigonometry camp that you feel like it would be important to talk about?
Have you talked about repeated roots of polynomials and how cool they are?
We've talked a little bit about like multiplicity and stuff like that. But maybe I could go in that in a little bit more detail. If you do give me a minute here, I think I am going to step away for just 1 second. And I'll be right back. It's time to feed the animals. And then we'll jump back in and we'll talk about those sorts of things. Be right
Does
back.
that mean it's going to be complete chaos for a few minutes?
No, you're gonna manage it all. You're gonna keep it together.
Oh, I'm managing it all. Okay, great.
Yeah. Have fun.
Bye. Hi, chat. How have all of your days been, chat?
Hey, it's me, Talos. I'm back.
Talos is back? Oh, wait a second. Oh, I see what happened. Oh my gosh, that comes through Discord. That's crazy. Intelligent Fool, hi, how are you doing? Oh, hi, Obi. Welcome in. That's Hurdy. I talk about soup? Like a madman. What kind of soup should I talk about? Chowder? That's good to hear, Intelligent. That's good to hear. How am I doing? I'm doing great. Samoyo, hi! Welcome. I guess I should be the one welcome because I came a little bit late because I was at work. But it's good to see you. Yes, throw all of the shapes, please. Throw them all. So many platonic solids. But I'm doing well, Obi. We got through the first week of classes. If I can get through week 2, I think it'll be smooth sailing. These first couple weeks have been really, really stressful for administration stuff. Yes, we got a good outfit. Nice. So anyway, chat, what's your favorite kind of soup? All these platonic solids and no romantic solids. Oh my god. That's so sad.
So yeah, I guess I'm back. Pen, just while we're here and we have just like a tiny break, do you want to talk about kind of what you're doing and kind of what's going on in conjunction with this little kind of calc thing that we're doing here? Or introduce yourself for anyone who might not know you.
Oh, sure. Hi, everyone. My name's Pen Center, and Talos and I go way back. Go like many, many years back.
Yeah, like,
Should I tell the story?
is there a story? Sure, go ahead.
It's like one day, what was that game we used to play all the time? That like card game. That was so funny. Oh, was it Code Names?
We did play Code Names, yeah.
Is it Code Names? Oh man, we should do that again. That was such a good time. I think
I-
that's when we really we really like kind of bonded as like a community over games like that.
Yeah, it was. I originally met Dawn, and so I've always streamed with like the math tag and stuff like that, because I do math help even just beyond kind of like dedicated math streams like this. But I originally met Dawn because some people from Dawn's community found me through the math tag, and then I found Dawn, and then Dawn organized Code Names, and then I met you and Obi and everybody.
And then we played like Played Up, and I was terrible at it, and it was a great time.
It was really hilarious.
But yeah, so while you're having a little break, I stream math over on my channel as well, and it was actually really fortuitous timing. Like, so Talos approached me and was like, "Hey, like I have this cool idea about doing an exploratory calculus class," and I said, "Cool," because I have this idea about doing a real analysis course with the Simple group, which is in the mathematics server. So we kind of tried to coincide this as best as we can. So we're still doing a little bit of organization over in the mathematics server for the real analysis portion of kind of this joint adventure. And we're hoping to get that started hopefully next week with the first presentation. So doing some real analysis with calculus focus. So really diving into sequences, series, derivatives, continuity, all of those topics explored through sequences and series. And then doing a little bit of proof stuff over there as well, like how to read and write a proof.
Yeah, so ultimately, while, in theory, this course will be kind of good for giving sort of like the standard sort of approach to calculus as typically learned after pre-calc and trig. And when you ever you take like an AP class in school or like a class, oh my god, in university or any of that sort of stuff. But there's many other ways to approach it too. And there will be some things, and I'll point it out whenever we get to them, that are sort of like hand wavy to a certain extent, where of like, well, we talk about like we'll get to the point where probably starting next time we meet next week, or yeah, probably next week, we'll talk about like limits and things like that, and really kind of like trying to kind of give meaning or like definition to what does it mean to like approach a certain value. But we're not going to get entirely into it. There is some sort of like logic behind limits that isn't going to end up fully defined the way that we approach them here. And so if you want kind of the deeper, more rigorous kind of like definition of limits and things like that, that's where something like Penn Center's, thing that he's organizing is going to be really good. Because then you gotta get like the, what's it? It's the epsilon delta definition of a limit.
Yeah, we go into that kind of nuts and bolts a little bit more.
Sip some soupin'. Okay, but yeah, so...
did you know... Okay, did you know that there is a soup in mathematics? S-U-P. We might talk about the soup in the real analysis course.
The soup. Okay. You don't want to have to read Russell's Principia in order to progress. Yeah, exactly. It's not important necessarily to know everything, but at the same time, it's like you should want to know everything, maybe. But it's just like, you're not gonna get everything from me. Not this time, not in these 12 weeks. You can go at everything from Penn Center. Penn Center will teach you everything.
I don't know if I can do that, but...
And so let's talk about polynomials and things that have repeated roots, and specifically kind of like what impact does it have whenever we have like repeated roots. And so to kind of get into it, what do we mean when we talk about like a root? Or, sometimes they're also called like zeros. or, solutions to a function, where if you're given some polynomial and you're asked to solve for x, usually it's basically like you take that function, you're setting it equal to 0, so you're saying its output would be 0. And so then you're wanting to basically find what's effectively the x-intercepts of the function. And so if we have something like x squared plus 4x plus 3, we haven't even covered factoring polynomials yet today. How did I miss that? Well, basically the short version is here. Something like this can factor to x plus 3 times x plus 1. And so this is like saying we have x plus 3 all times x plus 1 equals 0. And so then the question is, okay, well, for what values of x does this actually end up equaling 0? Well, we can look at this section here and say, okay, well, if this section right here is equal to 0, then it doesn't matter what x plus 1 is equal to, because 0 times anything, and so this could be anything, will still be equal to 0. And then similarly, if the section that's x plus 1, if this section here is equal to 0, then it doesn't matter what the x plus 3 is equal to, because 0 times anything is still 0. And so we would say the solutions for this equation here, the values that make this equation equal to 0, or this expression here equal to 0, would be when x is equal to -3 and when x is equal to -1. And so a lot of times in schools, they kind of gloss over this and they just say, okay, you take this and you're just going to take this one and it'll be the opposite sign. But this is why. And so, you take this and it's like you say, okay, x plus 3 equals 0 and x plus 1 equals 0. So that means x has to be -3 and -1. As far as kind of like, what do you do, like how do you factor these polynomials generally? And so usually the way that I kind of like to start and build this up is to first just kind of start with multiplying binomials. And so if we have something like x plus 1 times x plus 2, then we can multiply this out following basically just the distributive property. It's like we're, normally, like very generically, if we have something like 3 times x plus 2, we would say this 3 gets distributed into here, and so this will be 3 times x plus 3 times 2. But we can do the same thing here, but now instead of distributing like a single value, we're distributing this entire x plus 1. And so this x plus 1 gets distributed to the x, and the x plus 1 gets distributed to the 2. And so that would mean that if we kind of expand this out one step, then this would be x times x plus 1, and then plus 2 times x plus 1. And then we can even distribute these individually as well. And so we can distribute the x into here, and the 2 into here. And so that'll give us x times x is x squared, x times 1 is going to be x, 2 times x will be 2. I'm sorry, 2 times x will be 2x, and then 2 times 1 will be 2. And now if we combine like terms here, then we get x squared plus 3x plus 2. Zevran gave me money? It's not that they gave you money, it's that they gave me money. But by giving me money, now for the next month, you don't have to watch ads and you get to use emotes. Also, I should have said thank you, Zev, for the 2 gift subs to Deterty and Ultimate Doom. Very generous of you. And so now here we can kind of see, the process for distributing out, like these binomials. Now, what if we kind of look at distributing out these binomials kind of in general? Now, instead of like 1 and 2, what if I look at this instead of like x plus a times x plus b? where a and b can just be like any real number. And so if we expand this out, well then this will end up being x times x plus a plus b times x plus a. And then if I multiply this out, this will be x squared plus ax, and then plus bx plus ab. And then from here, one thing that we can do is we can factor an x out of this middle section right here. And I'm going to write it in a way that's maybe a little suggestive, where it'll be x squared plus a plus b all times x plus ab. And so what I want you to notice here is now we've written this where we have a polynomial who, it's important to note, has a leading coefficient of 1, but the middle term is some numbers a plus b, or the coefficient of this middle term, and then this term on the end. Obi-Wan Pez, thank you for the follow. You weren't followed? How'd that happen? But a times b is this constant term on the end. And so we can actually use this kind of as an idea for polynomials who have a leading coefficient of 1 to easily go from this form kind of over to this form. And so if we have something like x squared plus 4x plus 3, like we had earlier, then it's kind of like you say, okay, what two numbers a and b are there such that a times b is equal to 3, but a plus b is equal to 4? That's kind of the question here. And if you think about it for a bit, usually the process that I follow is I first think about the factors of 3. Because if you assume that this can factor into like, just normal integers, then that means a and b have to be factors of 3. And so if 3 can be described as, 3 times 1. And that works out because 3 plus 1 is also 4. And so that means in this specific case, our numbers a and b are 3 and 1, because 3 plus 1 is 4, and 3 times 1 is 3. And so that means that this polynomial here is equal to x plus 3 times x plus 1. And if we followed the same process of, then taking this and distributing it out and combining like terms, we'll find we get right back to where we started. And so these forms are interchangeable. There are, other kind of tricks or other ways that you can sort of think about kind of factoring polynomials when the leading coefficient isn't 1. And so kind of my favorite is, it's usually called like the AC method or sometimes slide and divide, where basically you can exploit the fact that like the coefficient for the x squared term and the constant term, they have to basically be like they have to be able to break up into factors such that when you distribute everything and multiply everything out, the combination of those factors will in some way end up being like the middle term. And so perhaps like a good example that I could do, I guess let me think of like a good example first. If we have something like 2x squared plus 7x and then plus 3, then one way that we can kind of start to thinking about how this might be factored is kind of by doing what we call like just the guess and check method. Where basically like the idea here is that we know that if we have some values of like x here and then some values, like some real numbers here, that as we kind of like multiply this all out, that these two values here, so like the value here and here, have to be factors of 2, whereas the values here and here have to be factors of 3. And then it's kind of just a question of like, how do you configure them? And so this is kind of like where the guess and check part comes in. And so we know there's only one kind of good factor pair of 2. And so we can kind of start by saying we have like 2x plus something times 2, or just x plus something. And then from here, we know that these yellow spots, these yellow numbers, have to be factors of 3. And so it'll be 1 and 3 in some description. And here it's kind of like, this is the check part of guess and check. And this is just kind of to first kind of build up an intuition of how you kind of go about factoring these things. And so if we put like 1 here and 3 here, then if we distribute this out, this will be x times 2x plus 1, and then plus 3 times 2x plus 1. And then this will be 2x squared plus x, and then plus 6x plus 3. And hey, it looks at that looks like that works out, because x plus 6x will be 7x. And so this ends up being equal to 2x squared plus 7x plus 3. And so there's this kind of like methodology, or this intuition, where the terms in front of the x and the constant terms inside the binomials have to be like factors of this like highest degree term coefficient and this constant term. And so there is kind of like a, can you do another one like this and explain again? Yes. Let me think of another good example. So if we have something like 8x squared, and so I guess maybe something else that I should touch on just a little bit that will make this maybe a little bit easier to parse, is there is kind of like a shortcut to multiplying these binomials out. You may remember it, they may have gone over it in school, where there's like an acronym, FOIL. And FOIL stands for first, outer, inner, last. And so if I write that here, that's first, outer, inner, last. And that just kind of gives you kind of like a quick way to remember how these terms are going to end up getting multiplied together and then combined. And so like if we have 2x times x, and so 2x times x, and then 2x plus or times 3, and then 1 times x, and then 1 times 3, then we get all of these terms down here. And so 2x times x is 2x squared, 1 times x is x, 2x times 3 is 6x, and then 3 times 1 is 3. And so it kind of lets us sort of skip this distribution step. But once again, you can kind of see here that the 2x times x gets us this term here. And so like these two terms here end up making the 2x squared. Whereas only the 1 and the 3 really kind of contribute to this 3 here. Because for us to get the 2x squared term, we have to have, like it has to have 2 x's. It has to be an x times an x. Whereas to get the constant term, we have to have no x's. And so just 1 times 3 in this case. And so that's why you can kind of break this apart and kind of build up that intuition, knowing that the coefficients of the x terms inside your binomial have to be basically like a factor pair of the coefficient on the highest degree term in your starting polynomial, and the constant terms inside the binomials have to be a factor pair of the constant term in your polynomial as well. And so if we do like another example to kind of go through that all again, And so if we have something like 8x squared plus... Pen, give me a number.
17.
17. Can you give me a better number?
You need 8. Maybe 12.
12. So if I write 12x here, what will this have? What number will make this work?
Oh my gosh, you're asking a lot of me on a Sunday at 6 p.m.
No, I'm just thinking to myself. Because if this is...
I was also distracted by all the cuties in chat.
That's right, they are very cute. It's very distracting. Does 7 work? Oh, I guess let's find out. That might just be a random number. Let's just find out. I don't think this will work. How about I do... if it's that...
Will 4 work at the end? 12 and 4?
Hold on, perhaps I should just... I should just start with the factored pair and figure out what it will end up being.
Yeah, I think if you do 12x plus 4, it'll be okay. 15x plus 7, OB has suggested as well.
Alright, I got one. So 8x squared plus 26x plus 15.
That
And
was
so-
scary.
It does look scary, but looks can be deceiving. And so, once again, this is kind of just like one of those things where, for her to try, we basically like are gonna look at this leading term, and we're gonna look at this term on the end, and we're gonna consider the factor pairs of each of these. And so, factor pairs of 8 include 1 and 8, but also 2 and 4. And then factor pairs of 15 include 1 and 15, but also 3 and 5. And so that means that it's basically, assuming that this can be factored nicely, that it's safe to assume that it factors to some combination of like x on one side and 8x on the other, or 2x on one side and 4x on the other, and then like plus 1 or plus 15, or a plus 3 or plus 5. And so let's just try one. And so if we start, for instance, and if we make this like 8x and then say plus 3, and then times x plus 5, let's see where that gets us. And so we can see initially from these kind of first terms and these outer terms that of course we'll get 8x squared and 15, but then the question is, do we end up with plus 26? And so if I do 8 times 5, and so here, I'll write first that these will be 8x squared and then plus 15 on the end. But if we do the 8 times 5, that will get us plus 40x, and then the 3 times x gets us plus 3x. And last I checked, 40 plus 3 is 43 and not 26. And so this doesn't seem to work. And so we could try another pair, maybe instead of 3 and 5, or it could even be that 3 and 5 aren't like this, but it's in fact 3 should go over here, and 5 should go over here, which would get us 8 times 3, and then plus 5 times, or like 8x times 3 plus 5 times x. And 8x times 3 is 24, and then plus 5x will be 29x, and so that's a lot closer. but still not quite right. And so we tried both combinations for if it's 1 and 8 as our leading terms, then neither 3 and 5 or 5 and 3 work in those kind of respective orders. And so we could instead try with 2 and 4. And so if we have 2x, and then so if I just do like, I don't know, plus 5 here, and 4x, and then plus 3 over here. So we know that 2x plus 4x is going to get us 8x squared, and then 5 times 3 is going to get us plus 15 on the end. And so now the question is, what are the cross terms? And so 2x times 3 is going to get us plus 6x, and then 5 times 4 is going to get us plus 20x. And last I checked again, I'm pretty sure 6x plus 20x is still 26x. And so this one does work. And so, in other words, 8x squared plus 26x plus 15 is equal to 2x plus 5 times 4x plus 3. Clear as mud? Everybody got it? And so there is sort of an assumption here that, builds upon the fact that you do kind of have to assume that these polynomials can be factored nicely, when in reality, not every polynomial can be factored nicely. But usually whenever it comes to doing questions and stuff like that, as a note, you can check boundaries by looking at the closest factor pairs and the furthest away. But that's an AC method thing. Yeah, and so maybe it'll be good to kind of go from now the guess and check method to more of the AC method. I flipping love polynomial factoring. I think it's fun. It's kind of just like a little bit of a puzzle thing. And so there is a kind of maybe a nicer method to kind of factoring polynomials like this, one that requires less guessing and checking. And that's called the AC method, or sometimes it's the slide and divide method and things like that. And so the idea for this quote-unquote AC method is you start with your polynomial, and so in this case, 8x plus 8x squared plus 26x plus 15. Slide and divide is a false prophet. I can show why slide and divide works with the quadratic formula. But I do feel like slide and divide is a little bit too hand-wavy as far as algorithms go. And it leads students to saying things like one polynomial is equal to another polynomial that it's not actually equal to. And so I do dislike slide and divide as well. But the AC method is pretty functionally similar to the slide and divide method, really.
I don't know if I've ever heard of the slide and divide method, to be honest.
Well, we can talk about it in a moment. But the AC method basically is first you take your polynomial here, and what we're going to end up doing is we're going to multiply the leading coefficient onto the constant term. And so we'll figure out what 8 times 15 is. And so 8 times 10 is 80. 8 times 5 is 40, and so 8 times 10 is 100, so 8 times 15 is 120. And then we take that 120, and what we're looking for is a factor pair of 120 that adds up to make 26. And so adds to make 26. And so if we look at, kind of factor pairs that are already close together to each other, we can start with 10 and 12 would be 120, and that makes 22. And so we need there to be a slightly larger difference between the factor pairs. And so one thing I could do is to easily find more factor pairs, I could say divide 12 by 3 to get 4, and then multiply 10 by 3 to get 30. And so 30 times 4 is another factor pair. but that'll be 34, so we need to get smaller. So what if I double 8, or double 4 to make 8, and half 30 to make 15? And then 15 plus 8 would be 24, so that doesn't work. And at any point you can also like jump over to like another factor pair. So I could also say like, 6 times 20. Or what did I say? 24? It's 23, that's correct. 6 times 20 is another factor pair. That doesn't seem to work. How about... Let's see. Let's just throw Monte Carlo on it. What's another one? 24 and 5?
Can you explain something to me, Talos? You have 6 and 20.
Uh-huh.
And it looks like there's a little arrow that says like add to make 26. So why doesn't 6 and 20 work?
Oh, it doesn't work because I'm stupid.
Oh, okay.
No, it does work. For some reason, I just like glazed over that. Perfect. You've solved the problem, Pen. And so, and so where we go from here now is basically we can break this 26 up now into 6x and 20x. I thought Tally was just asking for more. I mean, in theory, you don't need to find more once you have the one that works. But so what we can do from here now is we can rewrite this as 8x squared plus 20x and then plus 6x plus 15. Or alternatively, this could be in the other order. It could have been plus 6x and then plus 20x. It's not that important which the order it's in. But then from here, we can group these off. And so we could say, this is a group and then this is a group here. And then if we factor each of these groups as much as we can, then ideally we should be left with a common term that we can pull out of both groups separately. And so from this group here, we could pull out 4x. And so that would be 4x times 2x plus 5. And then from this one over here, we could pull out 3. And so this would be plus 3 times 2x plus 5. And this is what we're hoping to see. We're hoping to see that both of these will have this like common binomial term. And so both of them have a 2x plus 5 in them. And so then we can take this 2x plus 5 from both of them and factor it out and pull it out front. And that will leave us with 2x plus 5 times our 4x plus 3. That remains inside. And so this kind of, I would say it works more consistently than doing something like guess and check, especially if you have like a lot of different possible combinations to try and figure out. But, factoring polynomials is the sort of thing that it's good to try and build up an intuition for. And so here, one of the intuitions that you can build for, something like figuring out which factor pair will add to make this. Another instance of using the term binomial. I mean, what? This is a binomial term, is it not? Or am I using that term incorrectly?
I think you're using it correctly.
I think so. There's a lot of binomials thrown around when you're factoring. But yeah, so it's like, thinking about, do you need the factor pairs to be closer together or farther apart to make this middle term here? And so, usually the smallest the combination of like the factor pairs can get is when they're like as close together to each other as possible. And so for like 120, the closest you can get them is like 10 times 12. And so just about like the smallest it can get would be like, 10 plus 12 is 22. And then of course you could get them really far apart with like 2 and 60. And so, that would be like, 62. And so kind of like getting an idea of like how far apart do the factor pairs need to be able to end up with the number in the middle here. Hey Femvox fan, welcome in. We are just reviewing factoring polynomials. And so sometimes you also get polynomials that are what we call perfect squares, where after you factor them, they factor to basically be like the same thing twice. And so if we look at something like x squared plus 4x plus 4, for instance, and then we kind of go back to our kind of original method of asking ourselves, okay, what multiplies to make 4, but adds to make 4? Well, then that'll be 2 and 2, because 2 times 2 is 4, and 2 plus 2 is 4. And so that means that this is equal to x plus 2 all squared. Sorry, just taking a drink of water. Hydrate or dihydrate, H2O-mies. And so, sometimes there are different ways that we can kind of describe different polynomials. So like in this case, this one is a perfect square because it's basically the same thing times itself twice whenever it's kind of all factored out. Another kind of common type of like polynomial is like a difference of squares. And so if we have something like x squared minus 4, so this one looks a little bit different now because we don't have like a middle term. But you could think of this as being like x squared plus 0x minus 4. And asking yourself like, what multiplies to make negative 4, but adds to make 0? And so like in this case, it would be like negative 2 and positive 2, because negative 2 plus 2 is 0, and negative 2 times 2 is 4. And so this one would end up being x plus 2 times x minus 2. And in general, you can kind of describe like a difference of squares. I spy a Sierpinski's gadget. Yeah, I love the Sierpinski's triangle. And so if you have something of the form that's like x squared minus a squared, this can pretty much always be factored to the form of x plus a times x minus a. And there's a similar formula for the sum and difference of cubes. And that one's kind of like a fair bit more complicated. Just a side note, there's a method called completing the square as well, which is related to this. Yes, and so usually I find it's a little bit better to talk about stuff like the quadratic formula and completing the square whenever it comes to like methods of like solving equations. You can use something like completing the square to like take something like, for instance, like take a standard quadratic equation and kind of put it into something like vertex form. So that it can be easier to graph. But generally, it's kind of, I would say it's, if you're just like factoring an expression, it's better, in my opinion, to try and use stuff like the AC method or guess and check, or just kind of like the standard factoring method, unless it's clear that it's not going to factor with like non-radical terms. And so there are other methods, such as using like the quadratic formula and using completing the square, that would let you factor a polynomial that doesn't factor nicely. And we can get into that a little bit too. And so as far as kind of like the quadratic formula goes, this is something that you've all probably kind of been taught or, had repeated to you several times before. But so for a like quadratic polynomial in standard form, if we can write it as like ax squared, ax squared plus bx plus c equals 0, then we can find x using this formula. And so x will be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so normal, like the way that I was taught this, it was like sung to me by like the tune of like Pop Goes the Weasel. I don't know how, like if people, you know, maybe even in like non-English countries are like taught like similar ways and things like that. But I was always like, remember this as like x equals negative b plus or minus square root of b squared minus 4ac all over 2a.
I'm not gonna lie, I'm really happy about your singing capabilities with regards to this formula.
Yeah, I mean, you know, sacrificing all shame and everything here to sing this for you guys. Not that I ever had any shame or anything to begin with. But yeah, and so this can let you kind of, you know, take any sort of polynomial and factor it. There are some cases where this section here, the square root of b squared minus 4ac, will end up being the square root of a negative number. And that doesn't mean necessarily that it doesn't factor, it just doesn't factor with real factors. There are things that we call like complex numbers, which you can use to kind of describe the square root of negative numbers, that maybe we'll get to tonight. But kind of the long and short of it is if we kind of go back to earlier where we had that there was a polynomial in factored form where if it was x plus 3 times x plus 1 equals 0, that means for all of this to end up being equal to 0, that x would need to be equal to negative 3 or negative 1. And so if I just told you that I have a polynomial where x equals negative 3, or like I have a polynomial that has solutions where x is equal to negative 3 and x is negative 1, you may not be able, like you can't tell me exactly what the polynomial is, but you can tell me that part of the polynomial can be described in factored form as x plus 3 times x plus 1. It just may then also be multiplied by some constant that we don't know. And so basically what we can kind of do from here is we can use the quadratic formula to find the solutions of a polynomial and then basically work backwards from those solutions to build the polynomial itself back up again. And so if we use our 8x squared plus 26x plus 15 as an example, these numbers are going to be kind of gross, but we can do it anyways. You know what, maybe it'll be better. Do I have a nicer one? This one.
Do you want one that's gonna come out with like an A up front?
Yeah, it's okay. I'll use this 2x squared plus 7x plus 3 one. That'll be a little bit nicer. And so here, in standard form, we could say that the 2 is A, the 7 is B, and the C is 3. And so if we plug all of these into our quadratic formula, then what we would get is that x is equal to negative 7 plus or minus the square root of 7 squared is 49, and then minus 4 times a times c, so that's 4 times 2 times 3. 4 times 2 is 8, times 3 is 24. There's a meganome. Get down, chat. Here he comes. I'm gonna die. Okay, and so we would get all this. Oh, and I can just write 2 times 2 on bottom is 4. And so 49 minus 24, what's that gonna be? 25. And so this will be negative 7 plus or minus the square root of 25 all over 4. And the square root of 25 is 5. And so this is negative 7 plus or minus 5 all over 4. And so that gets us two solutions. Negative 7 plus 5 will be negative 2. Divided by 4 is going to be negative... Or wait, what is it? Oh, yeah. Okay. And so that'll be negative 1/2. And then if we have negative 7 minus 5, that's going to be negative 12 over 4 is going to be negative 3. And so what we can say here is that if I told you that I had a polynomial that its solutions are negative 1/2 and negative 3, that I could write it as x minus 1/2, or sorry, x plus 1/2 times x plus 3. But you'll notice that this polynomial, like, we know that this one right here factors to be, like, if we were to multiply this out, x times x just gets us x squared. And 1/2 times 3 gets us 3 over 2. And so that's not going to be equal to this 2x squared plus 7x plus 3. And so what we need is to also multiply this by the coefficient that we had here originally. So this 2 that we had in front of our polynomial needs to come back for this to be actually like equal to this. And so this kind of comes from a fact of us dividing by a. And so when we divide by a, we kind of like destroy the information of that leading term. And so now, if we were to distribute this 2 into this one, just to get rid of this denominator here, then we get 2x plus 1 times x plus 3. And that will be equal to our 2x squared plus 7x plus 3. Ta-da!
That's really interesting, Talos. I never saw it like that before. I had always kind of thought about it like in terms of equations. And so that's where you end up losing that information about the 2. Like if this is equal to 0, for example, right, you can kind of divide by that 2 and it's not a big deal. But yeah, if
right.
you're just factoring, it is a big deal, right?
Right. Yeah, and so I mean, I learned it this way too at one point. Yeah, and so this is why I do say that the quadratic formula works better if you're solving for x. Because, I mean, that's its purpose. It gives you solutions for x. But it's also because, since that kind of includes like that dividing by that leading term and then kind of pulling it apart that way, if you're using it for factoring, you kind of have to be careful to kind of get that leading term back, in a sense, so that, the factored form is actually equal to the original polynomial and not missing like a constant term, or like not missing like a scalar of some sort. But yeah, and completing the square, is similar in that sense, where I find that completing the square kind of works nicest whenever you do have it equal to 0. And completing the square kind of goes back to what we were talking about before, where it comes down to like, some polynomials can be described as perfect squares of each other. And if we kind of start with, something like x plus a, and we just square that, well then as we expand this out, this will be x plus a times x plus a. And if we FOIL this, this will be x squared plus 2ax plus a squared. And so if we have some polynomial and we want to kind of like shoehorn it into the box of it being a perfect square, then like if I start with something like x squared plus 4x plus, I don't know, 7. Then if I compare these for a moment, well then we know if this middle coefficient here and this middle coefficient here kind of are like the same thing, then what we need is for the constant added to be whatever a squared is. So if 2a is equal to 4, then that means a would be 2, which means that if we can make this polynomial here, x squared plus 4x plus 4, then it would factor as a perfect square. And we can do that by just kind of a method of rewriting it. Oh, my pen tip fell out somewhere. I was like, why isn't it working? Okay, I got it. And so we could rewrite this polynomial here as x squared plus 4x, and then plus 4, and then plus 3. And so just essentially pulling the 7 apart into 4 and 3. And so now, if we look at this portion right here, this is a perfect square. And so we could factor this like a perfect square. And so we could rewrite this polynomial we started with, the x squared plus 4x plus 7, as x squared plus 4x plus 4 plus 3, which would then become x plus 2, all squared, and then plus 3. And this can be handy sometimes whenever you're solving like polynomials for x in ways where it doesn't factor nicely. So like if we had this x squared plus 4x plus 7 equals 0, well then this would still equal 0 and this would equal 0. And now we could try and solve for x. And so we could figure out what x needs to be for this to be a true statement. And so it doesn't work exactly the same as before. Like we can't just look at this inside and set it equal to 0, because if this is equal to 0, well then it's still plus 3. And 0 plus 3 is not 0, so that doesn't work anymore. But we can just solve for this directly now, because we only have like one x in this equation, and so we can isolate this x pretty easily. And so if we subtract 3 from both sides, then we get x plus 2 all squared, gets us equals negative 3. Now we can take the square root of both sides. Okay, well in this particular instance it actually isn't super nice, because then we get the square root of a negative number. And so what if I make this 7 a 1 instead? And then instead of being plus 4 plus 3, this can be plus 4 minus 3. And so now instead of subtracting 3 from both sides, we can add 3 to both sides. And so this would get us x squared, or x plus 2 all squared is equal to 3. And now we could take the square root of both sides. And one thing to keep in mind here, to be careful about, is that any number squared, or really any number to any even power, will actually always be positive. Or I should say any real number to an even power should always be positive. Because we know that a negative times a negative will always be a positive number, and a positive times a positive will always be a positive number. And so what that really means is that the inside of this stuff that we're squaring here, whatever x plus 2 is equal to, it doesn't matter whether it's a positive number or a negative number. It will always kind of, after being squared, end up being positive. And so what we have to be careful of here is, after taking the square root of both sides, being left with x plus 2, we have to account for the fact that x plus 2 could end up being equal to whatever the square root of positive 3 is, or the square root of negative 3. Because even if it was the square root of negative 3, after being squared, that negative will go away. And so this will end up being x plus 2 is equal to plus or minus the square root of 3. And then after subtracting 2 from both sides, we get x would be negative 2 plus or minus the square root of 3. And so completing the square is a nice way to, solve polynomials sometimes. If you kind of internalize the process of completing the square, it can be a lot nicer than using the quadratic formula sometimes. But it's just kind of always a question of like, how nice are the numbers actually? And
Alex, may I?
yeah, go ahead.
I'm wondering if it might be beneficial here to show everyone what x squared plus 4x plus 1 looks like as a parabola to make a connection.
Sure. I've got Desmos right here. And so x squared plus 4x plus 1. And so, here what we had before was that we got our solutions was x equals -2 plus or minus the square root of 3. And so you can see it's all kind of centered here on -2. But if we add the square root of 3 to that, well, the square root of 3 is a little bit less than 2 because the square root of 4 is 2. And so it's like we have -2 plus a little bit less than 2, or -2 plus a little bit, or like minus a little bit less than 2. And so you can see these solutions here. And so once again, as a reminder, when we take these functions and set them equal to 0, what we're really saying is we want to find the values of x where the output of our function is 0. And output meaning like our y value. And so our y value is 0 when x is -2 plus or minus the square root of 3. And so that's where we can kind of see these roots here. And so if we have like another, and so at this point, like another sort of thing that we can do is we can even start to kind of like build graphs by their roots, where, we know now from kind of everything that we've been talking about, if we have something like x plus 2 times x minus 1, then, and set that equal to 0, then x will be, or the function will be equal to 0 when x is -2 and +1. And so if I type that in here, so x plus 2 times x minus 1, and hide this other one, then you can see here it has these roots, these gaps, or these values that go through -2 and +1. I've always wondered, why does 4x move the vertex diagonally? Because I noticed it moved left 2, down 4, and the down 4 part kind of makes sense. But what about the left 2? That's an interesting question. And so, I mean, if we were to make like a correlation with completing the square and vertex form and that sort of stuff, then what we can say is that if we have some function that we can describe as x squared plus 2ax plus a squared and then plus k, and maybe it would be even better to write this as like, 2h and then h squared, then whatever this like middle coefficient is ends up kind of being responsible for like the left and right shift. And then just the h squared plus k, if you kind of subtract the h squared from the term on the end, then you get its up and down shift. And so, it's not as though the 4x is directly responsible for it moving diagonally. But it's kind of the combination of that middle coefficient with whatever you're adding on to the end will kind of move it. It's like as you increase... Okay, so this could actually be kind of cool to see. If we have something like x squared plus 2hx, and then plus h squared plus k. and I make sliders for these, then if I make k something like 4, then as I increase h, oh, it does just move left and right. Okay, but what if it's not plus h? What if it's just like this? Or not plus h squared. So yeah, now you can see it kind of has this almost diagonal-like motion. Because if we think about how this kind of like compares to its vertex form, then to get it into vertex form, we would have to subtract, or we would have to like pull the h squared value out of k to figure out where its new vertex will be. And so that means that as we increase h, the effective value that it's ended up like being shifted up will go down. And the same thing if h gets negative, then it's still going to be h squared, and so it still kind of ends up going down and to the right. I had never considered what the actual like impact is of just like increasing the value when it's in standard form. I've always just thought of it relative to vertex form, but that does make sense in retrospect.
Yeah, I always think about it as like the vertex almost looks like it's on a parabola or something like that as it kind of moves around, but...
Yeah, that might actually be true. What if this is negative x squared plus 4? Oh, that's k. I think that vertex is actually mapped onto like the parabola here.
So yeah, that's how I've always kind of like visualized it.
I never thought about it. Neat. This is magic.
And the fixed point at, what is it, 0, 4?
Yeah.
Like there's always a fixed point on the parabola you're moving around at 0, 4, right?
Right, and I guess that's based off of whatever k is.
Yeah.
Neat.
No, it's cool because this is something that like I don't think we ever talked about this at high school, and this is something that I kind of explored with students that just had these questions in calculus class.
Yeah. And now I'm getting to do it too. Okay, so like what else? We still never actually touched on, so how exactly do the two parabolas interact? So if I hide this one for a moment, so basically what I have here is just like I can even make this plus k too. And so this is just like some parabola where given the value of h, if I just increase or decrease k, then we can see this parabola moves up and down. And so this is kind of going back to when we talked about transformations earlier. If we're just taking the output of the function and we're adding a constant to it, that's just going to make the function move up and down. And so you can see it goes up or it goes down. And so that's really all we're doing by changing k here. But if we think about how we use completing the square to go from basically standard form to vertex form, where, this like x squared plus 4x plus 1, this ends up being equal to the x plus 2 squared minus 3. One way that you can think about what we're doing is we're figuring out kind of what h is, what that left or right transformation is, which ends up being half of this middle coefficient. And that's how we end up with the 2 here. But then to get the part necessary to actually factor it as a perfect square, we have to subtract h squared from the k on the end to essentially pull h squared and k apart, so that we can factor it as a perfect square. And so in doing so, what we see that happens is as we increase or decrease k, we end up effectively subtracting that value as we increase or decrease h, we end up subtracting h squared from k, pulling it apart to essentially be like a, like a perfect square. And so that causes it to move down as we go kind of to either side, kind of increasing or decreasing h. I know the vertex moves along the second, but how do they like combine mathematically or whatever? Why exactly does the vertex end up following a parabola? My intuition tells me that it has something to do with the relationship between h and k as they kind of like change with respect to each other, being like if k changes by 1, or if basically it's like if h changes by 2, k changes by 4, because it's we like they're separated by each other by like the value of h squared and k. And so if we were to like basically say like the amount that k changes by is going to be equal to h squared. And so that would be the same thing as saying like the amount y changes by is equal to x squared. And so the relationship between k and h is the same relationship as, like a function where it's equal to x squared or a function to the power of 2.
Yeah, I wrote this specific question down that you've been using because I think we can maybe formulate a really interesting problem for some people to explore a bit, and then maybe we could actually come up with kind of the algebra about why it works in the background.
Yeah. I think that would be cool.
Because I think it's a really interesting, like, this is a good question and a really interesting thing to think about.
Mm-hmm. I think that
it would
is
be fun to, like, really make a connection there, I think.
Yeah, I think the heart of it is in there in my statement somewhere, where it's just the relationship between as we increase h, k has to change by like the k in respect to the vertical transformation has to change by h squared.
Yeah, and that's captured by that parabola that you have at the very bottom, right? So that x squared negative x squared plus k, I think is really the relationship between h and k.
Right. And now kind of describing more explicitly maybe why this is true or where this comes from, I guess would be the problem. It's like I have that intuition that like h and k are related by this like squared relationship, but how do you actually like pull that out of the math and out of the equations?
Yeah, and I'm not sure if we can do it with basic pre-calculus or if we're going to need calculus to do it. So I want to explore it a bit more before I can give a definitive answer.
Right. Well, so we've been going for 2.5 hours. There's still a few more things I think to get to from here. Last couple things that I feel like would be really important for us to touch on is kind of where this talk about polynomials even started, which is like polynomials with repeated roots. And we can spend a little bit of time from that also talking about like quadratic inequalities and stuff like that. I think that would be good too. And then we can review a little bit of trigonometry. And so on Desmos here, so we know now how to basically kind of like, we can essentially like build a polynomial of some sort, and we can basically like define what roots we want it to go through. Like if I say, okay, we have x minus 2 times x plus 1, then that's going to end up giving us a parabola that goes through positive 2 and negative 1. And we can see those roots here on the x-axis. If the standard form is ax to the power of b, do you mean ax to the power of 2? For like a quadratic? Maybe that b would be, maybe that b as a variable would work. I don't feel very confident in that, because where the relationship came from before has to do with factoring it as a perfect square. But if you have something like ax cubed plus cx plus d, then I don't know that, like, it's not as simple as kind of completing the square for that, is my first thought. I think there would be a different relationship between them. But maybe that's an even better question. Maybe it's like, how do you describe that in generality? But anyways, moving on. And so we know now how to essentially like build graphs of functions that we want to go through specific routes. Like I could add in as many routes as I want. If I want this to go through x equals 4, then I can make like multiply by x minus 4. Or if I wanted to go through -3 as well, then I can multiply by x plus 3. And so, of course, the shape of the graph gets more and more crazy kind of the more routes you add. And so like, maybe I can like divide this by 16 or something. And so we can make functions and things like that that kind of go through any x value that we want on the x-axis. But there are different ways that something can go through the x-axis. Or I guess you could even say not go through the x-axis. And so it comes down to like the multiplicity of the roots, and basically like how many times, what I mean by that is like how many times the root actually shows up in the factored form. And so if I get rid of a couple of these, and I just make this times x plus 1 again, well, in this case, x plus 1 occurs in this polynomial twice. And so we can see that there's something different about what the graph does when x is equal to -1 here. Before, if it was just x plus 1 without that extra factor, it goes through the x-axis. But here, with two x plus 1s, it does something different. Instead of going through the x-axis, it appears to bounce off the x-axis. But it still goes through at x minus 2. Or I'm sorry, x equals positive 2. And if I add another x plus 1, then it will do something different yet again. Where now, instead of just going straight through the x-axis, it kind of goes through the x-axis in this sort of S shape. And so one sort of intuition that you can sort of have from this is, you know, kind of like before when we were talking about the parent functions and stuff like that. If I had like x plus 1 squared, or if I just have like x squared, it has this kind of parabola shape where it bounces off at some point. And if I have x cubed, then it kind of has this S curve through this point. And so you can kind of extend this to the structure of these polynomials, where another way that we could have written this would have been x minus 2 times x plus 1 all to the power of 3. And so it's x plus 1 cubed, because that's x plus 1 times x plus 1 times x plus 1. And so you can see that it almost has this like cubic behavior here at this root, where it does this sort of S curve that you would expect of a cubic function. Or similarly, if I make this to the power of 2 instead of the power of 3, then it's like if I were to zoom in here, the x component of the vertex of a quadratic polynomial is also the average between the first and second root. Yeah, that's kind of like that's how the axis of symmetry works. And so because, you know, parabolas are symmetrical. But, what was I saying? Oh yeah, so here if
you're talking about this like, yeah, this really cool idea, and like I'm so happy that you hit on it. It's like, this is what we try to do in calculus a lot, is like I call it the calculus magnifying glass, where we zoom in and we talk about something like local behavior.
Yeah,
and
exactly.
I'll let you talk about it a bit more. Yeah.
And so it's kind of this, like here we have x plus 1 all squared. And so it's almost like there's this, if we look at around where x is equal to -1, we have this almost kind of, it looks parabolic essentially. Like if we were to zoom in, it has this parabola shape to it. And so where it kind of does the same thing that we saw before of our parabola, where it kind of bounces off at some point. And so just like here, it seems to bounce off at some point. Or if I even go crazy with this and make this like x to the power of 8, and then I were to also graph x to the power of 8, then these still look kind of similar. Where, you know, we can see this x to the power of 8, it still kind of goes, bounces off, but it's like super squashed at the bottom. And the same sort of thing happens here, still at our root, where if this root is at like, you know, to the power of 8, then it's still kind of like, if you were to look at it closely, kind of ignoring the things around it, it also kind of looks like a function that's to the power of 8, like to the 8th magnitude or whatever, 8th degree. But there's, you know, kind of like an underlying reason, I would say, to kind of like pay attention to with sort of like these multiplicities. You know, not necessarily to what I just brought up, but you can kind of like think about why, you know, this sort of thing happens around these roots. Why it's either like it seems like it goes through the root and it goes from like the function being negative, i.e. like below the x-axis, to being positive, which would be like above the x-axis. And one thing to kind of like think about, just to kind of like put in the back of your mind somewhere, is like how do we go from being like, it might sound like a simple or trick question, but it's just like, how do we go from like a function being positive to being negative? Like, how do you describe that? Or like, what has to happen for a function to go from being positive to being negative? And kind of like the short version is that, you know, for a function to go from positive to being negative, it has to cross through 0. And that's like kind of like a key point to kind of keep in mind. And there's lots of different ways you can kind of apply that fact. And so like over here, if we look at the function, you know, it's positive up here, and down here it's negative. And for us to get from this point to this point, assuming the function is continuous, we have to kind of go through 0 like this. And so you can think of every point on the function where it ends up equaling 0 as being like a important point where on either side of this value where it equals 0, the function could do one of two things. It could either stay the same, like it could stay negative if it was negative before, or stay positive if it was positive, or it could go from being positive to negative, or go from negative to positive. And so it's kind of like there are points where you have like options. And so like here, if I make this x plus 1 squared again, then you can see that we get this point where, you know, here at x equals -1, it stays negative. But here at x equals 2, it goes from negative to positive. And so,
Talos, I'm just going to say thank you very much for the invite. I do have to jump off for the evening.
okay.
Fem and I have come up, I think, with a reasonable solution as to why the vertex follows a parabola. I did post it in the Argos just in case Ultimate Eat wants to go and have a look.
Okay, awesome. Yeah, fun question. Well, thanks for joining me, Pen.
Man. You're very welcome. Should we try to do the same time, same place next week?
Yeah, I'll be here anytime you want to join. And so you can just let me know and you're welcome to hop in.
Oh, amazing. Thank you so much.
The turdy says good night and have soup.
I think sushi's on the menu tonight, but thank you very much, Dirty. We'll talk to you later. And good night, chat.
Good night, Pen. And so from here, we can start to kind of, like, there's another type of question that we can ask ourselves it's important to know how to do, you know, whenever it comes to calculus and stuff like that. And it's like we can ask ourselves, when does this function here, when does x minus 2 times x plus 1 squared, when is this less than 0? And so one way that you can kind of think about this intuitively, one way that you can kind of break down this question is it's like saying, okay, well, this right here, this whole function, or like this, oh my gosh, this whole part right here is our function. And so you could think that this is f of x. And so it's kind of like what we're asking ourselves is, when is the output of our function less than 0? In other words, when is f of x negative? And so, pretty simple, it's negative when it's below the x-axis. And so that would be like this section here, where the graph is below the x-axis here. And that it would not include this section up here. But there is one important thing to mention here too. I didn't say when it's less than or equal to, I said when it's just less than 0. And so there is this key point right here, where when x is equal to -1, it's actually equal to 0, which would be not less than or equal, like 0 isn't less than 0. And so here for like this particular function, we could say that it's less than 0, you know, from 2 to -1, and then from -1 to infinity, or negative infinity, not including -1 to 2, or negative infinity to -1. And we can do this for kind of like any function too. So like if I describe this as like f of x is equal to this, and then I can just write this as when is f of x less than 0. Turn the opacity down on this a bit. Maybe 0.1. And so, you know, if I change this now, so if it's just +1, so not to the power of anything, then you can see it shows us this is the range now where it's negative. As long as it helps me develop some intuitions for graphs and stuff, that's good. Yeah, I mean, even just like the browser version of Desmos, you know, I use it a lot and it even works pretty well on my phone. And I mean, we're using the browser version right now. But you can see here, like it's showing us, okay, f of x is less than 0 between here and here, which makes sense because if we look at the orange line, this is the section of the graph where it's below the x-axis. And if I were to add in another factor here, so x plus 3, then we can see now we have kind of two ranges. We have two intervals where, you know, if we just follow the orange line, on this section here, it's below the x-axis. And then on this section over here, it's below the x-axis. And so, as I kind of talked about earlier, the zeros of the function kind of give us opportunities to go from, you know, being positive to being negative, or being negative to being positive. And so one way that we could do this algebraically is if we had this function, you know, x minus 2 times x plus 1 times x plus 3, and we wanted to know when this is less than 0. Lassitude, no fun, thank you for the follow. Welcome to the Argonauts. Hope you're having a wonderful day. Then what we really can do is we can sort of make like a number line here that has all of our important points on them. We can call them critical points. Critical points is normally what they're called kind of in math. Where from here now, we can say that, okay, this function will be equal to 0 when x is equal to -3, x is equal to -1, or when x is equal to 2. And so these are our zeros. So these are our like opportunities where the function has a choice of going from positive to negative, or from negative to positive, or staying positive or staying negative. And so we can essentially investigate the function in each of like these sections here, between these values and outside of these values. And so if I check here below -3, so if I were to plug, say, like, here, let me do a different color. If I was to plug, for instance, say like -4 into here, and then over here I could do like -2, and then between these I could do 0, and then over here I could do 3. Then if I plug -4 into this, it will obviously still be negative. And so this will be negative, and then -4 plus 1 will be negative, and then -4 plus 3 will be negative. And so a negative times a negative times a negative will end up being a negative number. It's not important that we know what the number actually is, but we just want to know whether it's negative or not. And so we know down here, on this side of -3, this interval will be negative. And then we can do the same thing for -2. And so if we check between -3 and -1 by plugging in -2, -2 minus 2 will be negative, -2 plus 1 will be negative, and then -2 plus 3 will be positive. So a negative times a negative is a positive, times a positive will be a positive, and so now this interval is positive. And then if we continue with this, 0 minus 2 is negative, 0 plus 1 is positive, and then 0 plus 3 is positive. So that's a negative times a positive will be a negative. I'm a little confused about what exactly. Is there something specific that you're confused about? And if we plug in x equals 3, all of these will be positive. And so a positive times a positive times a positive will be a positive. When is it positive exactly? Okay, so between -3 and -1. Okay, wait. I'm waiting patiently. I'll take a drink of water. And by water, I mean brown water with coffee particles dissolved in it. So these intervals are like specific examples. So these intervals here, the -3, if I delete this one, the -3, -1, and 2 are from setting this equal to 0. And so note how kind of like earlier we were talking about how the points where our function equals 0 are essentially like opportunities from our function to go from positive to negative or negative to positive. And it's another thing that's like kind of important to mention, that between the points where these functions are equal to 0, it can't change from being positive to negative without crossing through 0. And so for us to go from negative to positive, at some point we have to go through 0. For us to go from positive to negative, we have to go through 0. And so we find the zeros of our function, the roots of our function, and then we investigate the area, like the intervals between those roots. And so here, our roots were at -3, -1, and 2. And so we are investigating the intervals between and outside of those values. Does that answer your question? And so what we found here is that below -3 and between -1 and 2, the function is negative. So we start from the left slash rightmost. You can start anywhere, technically. And alternate as the line crosses 0. So, sort of. And so here's where it's important to remember the multiplicity. So you've caught on to kind of a bit of a shortcut where the behavior as the graph goes through its roots is consistent. And you can tell from looking at the equation whether it will actually cross and stay, like go from positive to negative or negative to positive. And this goes back to when we were talking about multiplicity. And so if I make this x plus 3 root right here squared, then you can see now at x minus 3, instead of kind of having this sort of typical, like go straight through it behavior. Unfortunately, I must leave now because I have to get up early. Okay, see you later, Yeet. Hope you have a good evening. If you want to watch the rest of this, the VOD will be made available once the stream is over. But now you can see, since this root has an even multiplicity, and so this x plus 3 all to the power of 2, then instead of basically instead of crossing directly through the x-axis when x is equal to negative 3, now it bounces off the x-axis. And so in this case, it goes from positive and stays positive. And so one way that you can like build upon your previous statement is the sign changes. So here, I'll write this. The sign changes when what even multiplicity? So like here, we have this x plus 3 term to the power of 2. And so we call the multiplicity of this root basically like its power. And you can think of it because it's like we have multiple of them. So this would be like x plus 3 times x plus 3. And so the multiplicity of a root is like how many times it occurs in the equation. And so the multiplicity, essentially like the power of the root, is even in this case. And so when it's even, it bounces off like this. It has this bouncing behavior. If it's odd, so if I make this to the power of 3, then you can see it goes through the x-axis again, but the shape in which it goes through the x-axis is a bit different. And so instead of going straight through the x-axis, it does this S-curve, just like the function x to the power of 3 would do an S-curve through the x-axis. And so if we kind of expand upon what Deterti was getting at earlier, instead of checking every single one of these intervals, because that can get a bit cumbersome or a bit bothersome, we can say that the sign changes whenever, or when the multiplicity is odd. And stays the same when it's even. And so if I have something like this, and so if I kind of go back to this example, then our roots will stay the same. Or if I make this one to the power of 2, our roots will effectively stay the same. Or I didn't need to erase that. But this isn't necessarily positive and negative like this anymore. And so now what we could do is we could check just one of these roots, or just one of these values. And so if we plug x equals 0 in, well then this will be 0 minus 2 is negative, 0 plus 1 is 1, or is positive, and 0 plus 3 is positive. But this is like a positive squared. "15 minutes for one sentence." Yeah. And so, but this is like a positive squared. And so what's going to happen is this term right here will actually always be positive. And so we really just have to worry about these ones. And so a negative times a positive will be a negative. And so that means when x is 0, this interval here is negative. Now, all we need to do to figure out what the other ones are is to kind of go from here and think of, like, look at the multiplicity of each of these roots. So when we're at x equals 2, the multiplicity of this root is just 1, which makes it odd. And so if the multiplicity is odd, then that's going to tell us that it changes. So our sign will change across this root. Whereas when the multiplicity is even, it doesn't change. Same thing here when we cross x equals -1. We look at the root for x equals -1, and we see its multiplicity is odd, and so it will change again. So it goes from negative to positive. And then here, when we cross x equals -3, the multiplicity is even, and so now it doesn't change, so it stays positive. Can we even have multiplicity for the y-axis? So like we have a 90-degree tilted parabola? Yeah. And so that would just be writing the equations in terms of y instead. And so if I write x equals y squared, then now we have a parabola, but it's sideways. Or I can even write this like factored in like factored form like this. So this would be like y minus 2 times y plus 1. And then you can see we have basically the same situation, but just turned on its side. And if I make this y plus 1 squared, you can see the same sort of behavior, just all sideways, where when y is equal to -1, it still bounces off. Is there something we can't graph in a Cartesian plane? Yes. There are lots of things that we can't graph in a Cartesian plane. But it also just kind of like all depends on how you represent it, right? I mean, does a Cartesian plane only include like real numbers on its axis? Well, then you can't graph complex numbers. You know, how many dimensions are you going to have on a Cartesian plane? Like, you can't graph something where you need to like describe the output for like, you know, inputs and outputs for 3 variables on a like in a single plane. You would need 3 dimensions for that. You know, any sort of like if you have like a number space that's like toroidal or anything like that.
fx equals x 2 x plus 1 x plus 3 3.
Oh, lovely math puzzles. It seems like you're missing something in that function. Maybe you meant to add one of those sneaky, shiny things that join expressions, and you know, the thing that's like a bridge, not actually a bridge connectinator. Anyway, while you're fixing that, don't mind me admiring the lobsters and contemplating why government agents are obsessed with my cute evil plans. Yep.
Yeah, I mean, I don't know that there is necessarily anything that you like. There's probably something two-dimensional and defined strictly by real numbers that is not graphable in a sense. But it's kind of like a complicated question. A topologist would probably know. Like a topological space that, like a number space represented by a like non-orientable manifold that doesn't fit in 2 dimensions. like a Klein bottle number space, or like a Mobius strip number space. Be a topologist then, and one day answer my question. I love the idea of topology. I do want to learn it. Dirichlet's function would be very difficult to graph. Who's your favorite scientist / mathematician? I don't know. There's a lot of good ones. Like there's Richard Feynman. There's Marie Curie. I mean, Euler deserves a lot of his praise that he gets. Not Newton. I can tell you that much. Not Feynman, he was questionable. Well, I guess then, you know, I'm not well equipped to answer the question because I don't fully know the history for everyone. Why not? I mean, Newton was just kind of like an asshole, right? And, you know, kind of like manipulated like the academic council to try and like deprive Leibniz of like the joint discovery that they had. Anyways, a smart asshole though. Yeah, I mean, that's true. Who among us isn't that much of a smart asshole? Leibniz notation is said to be better. I do think Leibniz notation describes a lot of situations better, and we'll get to that. That's going to be something that we're going to talk about in this course. I think I'm neither. Yeah, you're not an asshole, Niche. I won't say that you're not smart, though. Okay. I hate your Newton hate. Well, I hate that you hate my Newton hate. So I think that kind of sums up really kind of a lot to talk about with pre-calc. Maybe it would be best. And so does anyone have any kind of like further questions kind of regarding, you know, everything that we've covered about like, you know, functions, like polynomials, all that sort of stuff. You know, whenever we kind of get into limits and things like that, we'll kind of return to rational functions, and kind of rational functions in the context of limits and that sort of stuff. If there aren't too many questions kind of about like this pre-calc review sort of things, we'll move into a bit of a review of trigonometry now. Are you considering becoming a topologist? I'd like to study topology. I think topology is really interesting. Unshackled by the concepts of dimensions. Total points spent on Captain of the Argo is equal to 279,725. I wrote a Python script. Well, because what would it be? So how much does it cost right now? Captain of the Argo now costs 1,675 points. And so that means the last time someone's paid for it... Okay, the last time someone spent points on it, it was 1,675 points. And so if we divide this by 5, that means that it's been redeemed a total of 355 times. Now 356 times. And so we can calculate the triangular number for 366. And so that would be 336. It's actually 335. I wrote it correctly. So this would be 336 times 337 all over 2. And then times 5. Now 337 and 338. No, my pen tip fell out. And so 337 times 338 divided by 2 times 5. Yep, that's 284,765. So that's another way you can calculate it. Maybe your Python script like just adds them all up. But if you know the math, TM, and know that you can think about this as like a triangular number multiplied by 5, instead of needing like a script to do a bunch of adding, you could just make it a function. The math, TM. Okay, well, let's talk about some trigonometry. Let's see how much of this I can get through before I totally crash out. Hopefully we can cover trigonometry today. So, best place to start with trigonometry is right triangles. Can I make a right triangle? No. So, right triangles. So like, what is trigonometry? Where does it come from? Who cares? So if we have a right triangle, just believe me for a second that this triangle is a right triangle. Just, use your imagination. If we say that we have some angle of this side right here, what they discovered back in like the days of the ancient Greek mathematicians and all of that stuff, is that the ratio of these side lengths always gives you like some function of the angle, or it always gives you like the same value. And we can describe that value with respect to the angle. And so if we label these sides here, and so if we say, this side's our opposite, this is our adjacent, and this is our hypotenuse. Then what the Greek geeks found is that basically like the ratio of the opposite to the hypotenuse is equal to this function that changes with respect to the angle that we end up calling the sine function. And so we can say that like sine theta is equal to the opposite over the hypotenuse. I'm going to write this the other way around. And then we can say that the adjacent over the ratio of the adjacent and the hypotenuse ends up being our cosine function. And so cosine of theta is the adjacent over the hypotenuse. And the tangent of theta is the opposite over the adjacent. Yeah, I see Deterti in chat writing SOHCAHTOA. And so SOHCAHTOA is a mnemonic to help you remember this. And so SOH, that's sine is opposite over hypotenuse. CAH is cosine is adjacent over hypotenuse. And TOA is tangent is opposite over adjacent. And so that's one way that you can remember these trig functions. And so usually kind of the important, so there's kind of like two parts of trigonometry when we kind of get down to it. I guess maybe three parts. There's a bunch of ways you can kind of divide it up. there's like the trig functions themselves. And so what are the actual trig functions and how do they change with respect to theta? And what do they look like? And so we can kind of start with that using the basis of what we've talked about so far in terms of reviewing pre-calc. But then from there, there's this idea of like the unit circle to help you kind of internalize kind of like what are the values, like some of the key values of these trig functions, you know, kind of like where do they come from? How are they related to the original functions, like the trig functions themselves? And then there's also trig identities. And so we may not get to all of that tonight, but we're going to try. And so one thing that we can kind of think of, you know, maybe we'll kind of start with this analogy of the unit circle first. And so consider we have like an XY plane. Whoa. And then we have a circle in the XY plane. Give it up for circles. Out. I hydrate. And so if we were to kind of like zoom in here and look at a point on this, oh my God, how long have you been holding that one in for? If we look at like a point on this circle right here, if we say that this point here has like a hypotenuse of 1, and so like the distance from the origin is always 1. I'm gonna blow this up a bit. Then we can describe this point right here. You know, it's still like x comma y. But if we think about it in terms of like whatever this angle is right here, and viewing this as kind of like a right triangle, like this, then we get an interesting relationship where once again, if we say that this is like the opposite from the angle, and this is the adjacent from the angle, then we can say that the sine of theta is equal to the opposite over our hypotenuse. But in this case, our hypotenuse is 1. And we can say the same thing for cosine. The cosine of theta is equal to our adjacent over our hypotenuse, which once again, in this case of the unit circle, is 1. And so what we get is that the cosine of theta, in this case, gives us this adjacent, which maybe you can see is also just going to be our x-coordinate. It's going to be like this distance it goes out from here on the x-axis. And our opposite is just equal to our y-coordinate. This distance it goes up on the y-axis. And so another way, for all of the points on this unit circle, we can actually describe this as being like the cosine of theta, because that's our x-coordinate, and the sine of theta, that's our y-coordinate. And so something we didn't touch on completely is the equation of a circle is like x squared plus y squared is equal to r squared. And so for like a unit circle where the radius is 1, then this is just like x squared plus y squared is equal to 1. And so you can see that if I type that in here, so x squared plus y squared equals 1, we get this unit circle. And if I was to make this point here, that was like cosine of theta, comma, sine of theta, theta, or I guess I need to make this something that I can change. I'll just make this like sine of A and cosine of A. Then you can see, as I slide A around, we get these points on this circle. What happens if you enter x equals 1 equals 2? It'll be an error. It doesn't work. I was like, it's just like, it doesn't know what you mean by this. And so we can see here that cosine of A and sine of A do give us points on this unit circle if we let A kind of change around and move around. Let's see. You know, I really don't think we're going to get through all of the trigonometry between now and 40 minutes from now. And so I think maybe this might actually be a good place to call it for this week. And we'll come back and we'll go through all of the trigonometry next week and kind of get started on some limits stuff. Just speed it up. Yeah, but it won't be as high quality. And so we're definitely going to go through it. And so we'll just go through it next week, and then we'll kind of start to get into a bit more of the meat and potatoes of kind of the calculus stuff. And so I think that was good. If anyone has any questions, you can make a post in the Math Zone on my Discord channel. And we can kind of, go from there, and I can find time. And we have Ate time for a couple minutes. Where is she? Where is she? There you go, chat. She scream. Okay, well, I hope you've all enjoyed this. I had a lot of fun. Kind of any closing questions? Are you human or cyborg? I am cyborg, and not human. Okay. Well, you all have a wonderful evening. Yeah, I'm a toaster. I toast toast. I will see you all next Sunday. During the week, I play video games, and so if you like video games, feel free to stop in for that too. If you have questions, like math questions between now and then, feel free to stop by while I'm streaming, and if I have time, we can even go through them then. Doesn't have to be on Sunday. And I'll catch you all later. Good night.